and take a look at the liposome itself. Does everybody see that? So let me go ahead. So here's the whole thing. What we're going to do is the tumor vessels themselves that I mentioned before, around the tumor vessels, around the cancer grows so fast that these overlapping units that are like shingles on a roof, they're defective in that area. Does that make sense? So the tumor area has holes in it. What we're going to do is make a drug that fits in those holes. Does that make sense to everybody? We're going to make a drug that fits in the holes, and that's what we need to do. So the tumor vessels don't contain the same level of seal between the cells because they're diagnostically leaky. And people have known this for thousands of years. So, you know, in like back in Socrates' days or something, they discussed cancers, and they called those bloody masses, right? So this leakiness around that area is called the enhanced permeability, and permeability means a hole. And once you put something in, it can't come back out again. And that's one of the reasons that cancer mutates, because it doesn't get rid of waste products that well. So this is called enhanced permeability and retention effect. So I have this thing in here, you know, just an analogy. So in the tumor sites, they're like Swiss cheese. And we want to put our drug that falls into the holes in the Swiss cheese. Does that make sense? The surrounding area in your body doesn't have these defects. So here's a nice picture. So the nanoparticles in the normal vessels right here, in the left of the drawing, the normal particles don't fall into the healthy tissue. Does that make sense? But where we go, where there's the cancer, see, we see the tumor here shown in like the purple, then that has these holes in there. So now my drug that's going through the body, it can actually go into those holes. And when it goes into those holes, it goes into the tumor. Once it goes into the tumor, those drugs are of a certain size that they're going to be able to go through the cell membrane. And when they go into the cancer cells, they release the agent that ties up the DNA. Then the cancer can't divide anymore. Does everybody see that? So what you learned today is one method to cure some cancers. Does everybody see that? So naturally, people can't cure all cancers, but I will say naturally, or, you know, because you're younger people, really in my age, because I'm headed to retirement, right? So I'm an older guy. But when I was your age, if somebody had cancer, they were dead. And somebody said cancer, it was like a death sentence. Now, today in 2019, due to drugs like this, when somebody says cancer, people say, good luck. I think you're going to make it, man. And that's true. So, you know, the ability to cure cancer with different treatments, and I'll go back to like this slide, these specific drugs, what they're doing is they target different areas. So different cancers are more susceptible to looking at like cyclican A or things like this in these different areas than others. And the drug we're specifically looking at is the one that does this. So it's going to do some cancers more than others, and it's going to do things like Kaposi sarcoma. It does that really well, and that's what we're thankful for. So today, in that one specific cancer, type of cancer, Kaposi sarcoma, that we can cure that with this particular drug rather well. So this isn't a universal cure, but it is a methodology that's used a lot in different types of drugs. So again, here's another drawing. So shown on the left, this is the healthy thing where the cells overlap. And over here, shown in the black, that's like the cancer cells. So our drug's going to be able to go through those defects. Does that make sense? I wanted to get some cartoons in there so you can see the difference. So to a doctor, what do we want to do as a doctor? We want to kill the cancer, right? We want to kill cancer, but we don't kill the rest of the patient. And you guys have all seen people with cancer. What happens to them? Their hair falls out, they lose 35 pounds, they puke, they're sick, because when they're killing the cancer, they're also killing the patient. And that's just what people do now. I had cancer myself, and I'll tell you, it was insane. It was like medieval. I couldn't believe how insane it was, because when they were trying to kill that cancer that was in me, I'm telling you, they came close to killing me. it took me easily a year or more to be able to heal. I couldn't lift a gallon of milk. That's how weak I was. Because what they were doing is they were killing me when they tried to kill the cancer. This is better because what we're doing is specifically just killing the cancer, but not the rest of the patient. Does that make sense? For my cancer, the one that I drew the cancer card, right? So sometimes you just get lucky and get cancer. So I got lucky and got cancer. This particular cure didn't work for my cancer. So I had to have like radiation. And radiation is close to being like burned at the stake. It was just like insane. You don't want to have radiation. So, hey, don't smoke. I already said that. How about that? So a liposome, let's define that. A liposome is a nanoparticle, a man-made nanoparticle, and it comes from the Greek word lipo, which is fat, and soma, which is body. So it's a fat body. So basically what we're doing is we're making like a greasy donut. Does everybody see that? We're making like a greasy jelly donut, and the jelly's poison, and the jelly that's in there that's poison is going to tie up the DNA and kill the cancer. That's what our goal is. So phospholipids in an aqueous environment orient themselves in a thermodynamically stable form called a bilayer. So when we put this lipid paste, so we go buy, I'm going to show you, but we go buy lipid powder. It's basically like powdered eggs. So again, I'm using a lot of analogies here, so they're not, analogies aren't literal, so they're a story, right, to convey an idea. But we buy something like powdered eggs or powdered soy powder, and when we put that into water, it'll form these little donuts, but it forms all kind of different size donuts. And we recall from my discussion before, I want to have the donuts that are less than 100 nanometers. Does everybody see that? So I'm going to have to figure out a manufacturing methodology that I can reliably make my poison jelly donuts, which is the liposome, a certain size and a certain size distribution. And that was one of my first slides when I had the Venn diagrams. So I'm trying to hit those key items in my discussion today. So a liposome is an artificially prepared vesicle composed of a lipid bilayer. The liposomes can be used as a vehicle for administration of pharmaceutical drugs, DNA or RNA tags, and nutrients. And what's important here is we're copying nature, so the liposomes are biodegradable. Does that make sense to everybody? So we're doing, like, I think, really logical work here. I know this is a complex subject, but if you follow the main themes, this is actually a very, very cool story. I know it's complex, though. So we're video recording this. You might want to play it twice. And it's, well, for the Penn State guys, even the NSU guys, you can call me up, or I can do some kind of another Zoom or Skype or something to answer your question. Very, very interesting topic, right? So this is the liposome and what it looks like, and it's a cutaway version, right? So here's somebody made this, I think, in the Czech Republic from the notation down in the bottom, I think so. So over here is a drawing, and I like it. I like the colors. It's really cool, right? So it's like a cutaway version of like a jelly donut. And on the inside, that crystal is like our poison. Does everybody see that? And then that lipid layer, can you see that around there? I'll get my pointer. This is the lipid bilayer. Does everybody see that? And then on the outside is this fur. And we didn't discuss that fur. What that furry stuff on there is sugar. And basically what we do is we make a sugar donut. And if we put in a donut that doesn't have sugar on it, the body's like, hey, where's my sugar? It would see it as form an object. So basically what the sugar is on this outside, this pink sugar, that is like stealth technology. So that's called polyethyl glycol. And when we put that on the outer core of the liposome, we actually do with self-assembly. We'll put that on the outer core of the liposome, and the body sees that liposome with the sugar on it, and it doesn't send like white blood cells or anything to attack it and get rid of it, because there's a bunch of things in your body to get rid of foreign objects. So we can't send in like a naked liposome. What we do with the liposome is we dress it in a polyethyl glycol fur. When we do that, it'll stay in your body for like 3 days before it gets, you pee it out or whatever, your body gets rid of it. Does everybody see that? And if we didn't have the sugar coating on there, your body would get rid of it in 20 minutes. So importantly, let's go over this again. A naked liposome without sugar coating will stay in your body for 20 minutes. When we put sugar on it, it'll stay in for 7 days, or 3 days, I'll say. Does that make sense? So let me go back up to this drawing. What I'm doing is my liposomes are flowing through your bloodstream. They have to be in there more than 20 minutes, and they want to go through your body a bunch of times, because every time they go through where there's a tumor, there's a chance they fall into the tumor and deliver the poison. So you have to have the liposome stay in your body for days or a number of hours to give them a chance to fall into the defects. Does that make sense to everybody? So we have this time constraint. So a question is, why do I put the sugar on a liposome? And the answer is, I need that because it has to go through the bloodstream multiple times, because every so often, some's going to fall into the tumor. So the more times it goes through your body, the more it's going to fall in the tumor. So I'm delivering the dosage passively through these defects. Does that make sense? So it's important. I mean, one of the key steps to doing this drug, they didn't have this cancer drug for hundreds of thousands of years. Does that make sense? This is a drug that was developed 20 years ago in research because of nanotechnology. And the reason is this was so complex. So this is a complex story. But we need to define this drug and put the sugar on here. And when we send it through, it actually falls through and goes into the bloodstream. Does everybody, into the defective endothelial cells, the lining cells in the tumor region. And that targets the drug to the tumor only. And that's the holy grail. We want to kill the cancer, but not the patient. So there's all kind of crazy things happening here. Does everybody see that? This is a long but interesting story. So here's the phospholipid again, and that's in this core. Does everybody see that? That's what it's made out of. And here is the liposome itself. So this is the star of my presentation. Here's the drug. So what we do is we take this powder and we put the drug in with the powder, like the egg powder. That's the liposome powder. And we put it together with our doxorubicin, which is my intercalation drug that's in the center here. Then I put water in, and these jelly donuts form like bubbles. Does everybody see that? But they have to be the right size bubble to deliver to those defects. So here's what I'm doing. I can go buy from Sigma Aldrich, your favorite chemical supply company. I can buy liposome powder, and it's like 85 bucks. And so here's the links. You can go buy it, and it's made out of egg yolk. You can buy other stuff that's made out of soy powder. But here's the links for it. And when you buy this powder, basically you put the powder in a test tube kind of thing. And then you put in your drug, your water-soluble drug, and then you mix it up. And when you mix it up, that powder forms into these jelly donuts. Does everybody see that? Like this, it forms in this foamy stuff. And then what you do is you take that foamy stuff, and that's your drug. And what it did is the drug that you put in there, it captured that in the inner core. So when we put the foam, when we put the egg powder in there and the water and the drug, it's going to form into these energetically favorable spheres. And now they're all different diameters, though. That's a bad part. So they form in all these different diameters. So this is what it looks like, the schematic. Does this make sense to everybody? So I buy my dry lipid powder, I add my poison and the powder, and I put water together, and it swells together, and it forms these little spheres. Does everybody see that? But they're all kind of different sizes. The next point is, like looking at one of our first slides, we would have to have a narrow distribution of like 100 nanometer or 70 nanometer particles. And now we have a wide distribution of sizes. So basically what we're going to do is we're going to take all these different size jelly donuts, and we're going to push them through a screen, and they're all going to pop out the same size jelly donut. Does that make sense to everybody? So this is the extruder right here, and this is a guy's hand for scale, right? So in the middle here, what we do is we put a 100 nanometer screen or 70 nanometer screen, and we put my liquid juice in both of these hypodermic needles, and we pass them back and forth, back and forth. And every time we do, we make them into a different, we make them into a closer size. Does that make sense? So as we extrude them, every time we do that, we get closer and closer to my goal, which might be, we'll say 70 nanometers, for example. And that's, so when we first get our jelly donuts, they're all these different sizes. The one we want is this SUV down here, 20 to 100 nanometers, let's say 70. But we got these bigger ones, so we don't want them. So we actually crush them through that screen back and forth, and we form the 70 nanometer one. So the initial particle, the goal that we want is something here. See down at the bottom, like 100. In this example, it's 100. So we want 100. When we start out, they're all big. They're all like 1,000. Does everybody see that? Or 2,000, 3,000, whatever this number represents down here. So they're about this size. And that's too big because the cell wants to take things under 100 nanometers. Does everybody see that? So what we do is we pass them through that membrane 3 times. And then we start getting a distribution like this. When we do it 11 times back and forth, so now I take this stuff, see this MLV? I'm taking MLV, I put it in these tubes on either side, and I pass it through the screen like 11 times. And when I do, I started with these big pink things, and I get this small one, and that's the one I want at 100 nanometers. Does everybody see the manufacturing there? So I started with this big collage of all different stuff. Then I put it through the screen back and forth, and I get that specific one that I want. Does everybody see that? So I just made a cancer drug. Does everybody see? Everybody's in. I made a cancer drug today. So now when I made that drug, it's of that size that it can fall in these holes. Does everybody see that? That was my goal, is to make something that's 100 nanometers, because 100 nanometers is not going to go through these cell membranes, but where the cancer is, that 100 nanometer stuff is going to be able to breach these defects and then go in and then kill the cancer. So this is actually from the patent from this drug called doxorubicin, which I think is one of the first liposomal drugs that were approved by the FDA and EPA, et cetera. It has to be approved by all these places, and the drugs and whatnot. So this is the first one. So in the first picture, we have our sugar-coated liposomes, and the cancer, for your vision, is in the calf region over here in this guy's left leg. And we put it through, and you can see that we actually tagged it with a radioactive element, and we can see where the liposome is at in the body through an X-ray. So we're tracking radioactively tagged liposomes in the body. After 4 hours, it's all distributed throughout the body. Does that make sense? And in 4 hours, if you didn't have the sugar coating on there, you would pee it out or something. Your body would get rid of it, right? It would filter it out of your body. But we put the sugar coating on there, and it's staying in your body more than 4 hours. But it really is not going to the place that you want. But after 24 hours, we can see that it starts building up in this guy's leg. Does that make sense? Then after 48 hours and after 96 hours, we can see that that drug is building up in those areas. Does that make sense? So we delivered the liposome drug to a tumor in this guy's calf, his calf muscle on his leg. Does everybody see that? Or the calf area in his leg. It's a skin disease. So it's the skin on his calf. So then we do biopsies of, like, we do a biopsy of his thigh up here, and then the calf, and then the surrounding areas. And here's what it looks like. We did an area like shown in red. This is the normal skin near the tumor. And that's the amount of poison that's in there. Hardly any at all. Does everybody see that? And then we take a biopsy of the tumor and show how much drug is in there. Tremendous. Does everybody see that ratio? So what we want to do in cancer is cancer therapy. We want to kill the tumor, but not kill the patient. That's what we did right here. This graph, I bet you when they presented this to the doctors, people stood up and cheered and spilled their coffee and threw confetti. Does everybody see that? This is what you want to do. You want to kill the cancer, but not kill the patient. What does that do for you? When you have cancer and it's killing you, you can't fight off the cancer. Does everybody see that? There's secondary impacts of having that, like radiation. Radiation is damaging the patient, and you don't have the ability to fight off the cancer. So you're hoping you kill the cancer quicker than you're killing the patient. But with this particular treatment, you're getting all these advantages, right? You're getting localized cure. And that's what that's the big thing that everybody wants to see. So I hope you guys can appreciate that this graph, like people with cancer, like this is the graph we want for every cancer treatment. And this would be leaps and bounds. Well, this is leaps and bounds for this particular type of cancer. So this Kaposi sarcoma cancer. And this is a cancer that's found in humans, but it's especially prevalent in humans that have AIDS. So when you have AIDS, AIDS breaks down your protective systems in your body, the immune system, and you're more susceptible to getting this particular type of cancer. So this is a cancer that's related in some ways to AIDS, right? So this is important. Does everybody see that? So look at these slides. We're selectively delivering the drug, and then we're putting it in the area that we want. We're getting this ratio, and that's a cancer cure. So today's presentation, we learned how to, in this area, cure Kaposi sarcoma. And we did this strictly through nanotechnology. Does that make sense? So the tumor vesicles do not contain the same level of seal, and they're leaky. And this EPR allows the drug to go into the leaky sections. The doxorubicin, which is the poison, ties up the DNA, intercalates the DNA base pairs, and this shuts down the cellular division, and it kills the cancer. So what the liposomes do is they passively target the tumor area and cure the cancer in that localized region. Does everybody get that? So I know it's a long story. It's a very complex story, but you guys know it's not easy to cure cancer, right? The other thing I'd like you to think about, this is a very difficult presentation. In some ways, we went through it quickly. You know, I'm not requiring you to know that much, but actually to understand this presentation takes a lot of dedication, and it takes a lot of intelligence, and it takes a lot of understanding science. And I know if you go back to school, you know, depending on where you're at in your education, if you take a couple more years, you know, if you're a sophomore or something, you'd be able to go to a company and make these cancer drugs. That's crazy. So it's a really good thing going to school. You know, you could do this. You can understand this. Does that make sense? Maybe this presentation is hard because it's the first time you've seen it, and I understand that. But you guys have to see, you understand this presentation pretty well. And you take classes in nanotechnology and take degrees in nanotechnology, you can do things like this. Does everybody see? This is very, very powerful. So I'm really happy to give you this presentation to show you that when you go to school, you can do things like this. You know, you can cure some cancers now. And you could use these algorithms and your science to cure further cancers. So this is like really neat. I think this is a good presentation. So this is a review, right? And so here's a summary. Biological processes set the scale. So we pay attention to how big a size of a cell is. We make a drug as big as a virus. We make the drug stealthy. So, and then we design it so it only goes to where the tumor is. So nanoparticles such as liposomes are appropriate size and scale to interact on the cellular level for tumors, and they can you know, cure cancer. And again, I guess, you know, the overall thing here, I wanted to give you a presentation. You know, I wish I had 9 or 10 hours to talk about the subject to you, just liposomes. But, you know, this is a good presentation to show you that, you know, understanding nanotechnology and understanding biotechnology is a good pathway to use your nanotechnology skills and get jobs and benefit society. You know, so I think you should be really proud of, you know, being engineers and scientists, because we could do things like help people. You know, we can design drugs, We can make people healthy. We can make more efficient cars. We can make more efficient power generation. So we can positively impact the environment. We can positively impact the food cycle, the food chain. So I think your work in nanotechnology is important, and it greatly benefits society. So because engineers tough, and being a scientist is tough. So you have to have that realization that there's a reward at the end. So you make a sacrifice now, and your reward is the ability to do these things. Morally, it's good, and it also pays good. So then you could buy a big fancy car, jet skis, a house that's so big you don't even go in any of the rooms, and make your life so complicated that it's depressing. So you can look forward to that too, right? You can get a sports car, it's real fast, get a ticket and get put in jail. Does everybody see that? Go buy a Ferrari or something and get in prison. So look forward to that. We get a patent, have so much money you get in trouble. Does everybody see that? So that'd be good. So hey, thanks for paying attention to my presentation. So I'll open up the microphone for questions from you guys. So be rich, wealthy, and get in trouble. That's my wishes for you. Any questions here, guys?
Any questions here at Penn State? You can compose, or if you have a question.
I think this presentation is rather simple.
I can't hear the question if you'd repeat it, or I don't know if there's a question.
They appreciated, especially the level of the presentation, that they found it very useful and handy. Thank you, Terry.
I didn't think about this, and I could have done this at NSU State and all that other stuff too. I should have passed out jelly donuts today. That would have been creepy, huh? Yeah, I would have done the jelly, because I did the jelly donut analogy like 100 times. I should have put some. And actually, by my house, and I'm telling you, this is serious. In Pennsylvania, there's a lot of Amish, and I live in an Amish area, Amish community. They grow all like fresh raspberries and strawberries, and they make like homemade jelly-filled donuts, and they're like the bomb. They're just incredible. Like every morning I come to work, and they're in the field picking. Right now, it's strawberry season. So you guys here at Penn State, because I don't know in the other areas, but you should go to the farmer markets around here, because it's all fresh strawberries and stuff. So walk downtown. They have. Today's Thursday. I don't know if I think the farmers market is today.
Yeah.
Yeah, go down and get some berries.
Right.
And they have a lot of Amish down there selling goods and stuff, and fresh cheese and whatnot. It's really neat. Take advantage. I always think the simple things in life are the best, like a good cup of coffee or tea or fresh strawberries or a good donut. That's why you work hard. Mm-hmm. Those things are what makes life special, I think. Me.
So I think Joshua has a question here.
All right.
When you say that it ties off the DNA, does it like tie off the ends of it, or does it just stop the RNA from happening on the opposite side and creating the opposite
That's
side?
a good question. So, to draw a picture for you, let me go back up in my presentation so I can show you. A lot easier with a picture, I guess, if I could find it. So the DNA is like this. It's in number one. The DNA is together, and that's in one cell. But what it has to do periodically, it has to open up, and then a subsection of the DNA, they're going to make a clone of that. So the DNA is like a hard drive. They're going to like express an RNA piece, and that piece is going to be like a particular program. Does that make sense? And then from that program, they're going to write proteins. And that's one part of the DNA story. So you need to unzip it to do that. But also to unzip it in number two, it unzips the DNA into two sections, because when the cells divide, each cell needs a segment of that DNA. So basically you clone the DNA, and you have to have two DNA segments to have cellular division. Does that make sense? So basically what the doxorubicin does, or Doxil's the name of the drug. Doxorubicin is inside. It's like a tie wrap, and it'll keep this from splitting. Does that make sense? And if it doesn't split, it can't do the cellular division. So here's the cell cycle. if we don't have the ability to split the DNA into two pieces, then we can't have cell division. So basically, it's like handcuffs, and it ties that up just so it can't unzipper. It's like a zipper. So that's a funny story talking about Amish, because Amish aren't allowed to have zippers. So it unzips. So it has to break it apart like that. So you basically, in your mind, what it's going to do is it chemically ties it up like a tie wraps. Does that make sense or answer your question?
Yeah.
Mm-hmm.
So that's what it's going to do, is it's going to break this cell cycle that it can't divide. And then the definition of cancer is unregulated cell division. Well, you regulate cell division or make cell division 0. Therefore, like in English, by definition, you no longer have cancer because it can't divide anymore. And that's what cancer is unregulated division. So you know, as a logical statement in English, it's very literal what we're trying to do. And what we're doing is we shut it down at that point in DNA dissociation, so that we set down the cellular regulation point. Does that make sense?
Yeah,
And hats off to like electrical engineers, because they never seen any of this. Does everybody see that? So my area of research back in the day, this is a good point. I went to school for electrical engineering for plasma physics. But then I went to further thing because it was so interesting to do biology. So I went back to school and I took classes at Penn State, etc., and sat in on classes on biology because I have an interest in biomaterials. You know, so it's very, very, very cool, you know, and then teach the course. You know, you have to be fluent in multiple disciplines, right? So I'm just saying it's not my, I probably didn't even know what DNA really was till I was 30 years old. Seriously. So you can learn things later on, and you have to. So they always say engineers have to continuous learning. That's true. So, you know, because my area was plasma physics and antennas and waves and stuff like that. That's what I went to school for, you know, and plasmas and whatnot, and semiconductors. So semiconductor damage in plasmas is what my interest, my field is. But somehow I know about DNA because you have to. And it's interesting. How about it? I understand this thing. I'm real proud of myself because I understand it. It's really nice. Helped me when I had cancer. I did this before I had cancer. But when I had cancer, I understood a lot of things that were going on, you know, which was kind of helpful. Because getting cancer is really traumatic psychologically, you know. So you want to know as much going in because somebody will have it and then you could help them. You know, if you're the strongest person in the room, that's really good psychologically, right? So you help other people with their sicknesses and stuff. Really good. Be a good person. Any other questions, guys? All right, I guess I'm done. I'll turn it over to Oscar, and somebody called me up. I got to help them go fix a machine now. So I'm actually going to switch from biology guy to fixing some vacuum problem on a cell dehydrator. But I'll go do that, help them out, you know. All right, have a good summer here and enjoy the strawberries while you can. Take care.
Thank you, Terry. So let's give a 5-minute break and let's get together at around 10:55.